Okay, I think we are live now. Hello, everyone. Thank you for joining one more lecture of our PNS and processing in memory. Today, we are going to continue talking about real-world processing in memory architectures. In our previous meeting, in our previous two meetings, actually, you may remember that we were talking quite in depth about the AppMem PIM architecture. Recall that this is a DIM-based PIM architecture based on DDR DIMMs, and inside each of the chips, there are memory subarrays, and there are processing elements, which are general purpose in order cores called DRAM processing units or DPUs. You for sure remember this pictorial representation of an AppMem based PIM system where we see the host CPU, we see some DIMMs, DDR DIMMs that represent the main memory, and also we see the PIM enabled memory composed of AppMem DIMMs. And inside each of the PIM chips, we have 8 of these slices with a memory array, a 64 megabyte DRAM bank, and connected to it, we have a DPU, a pipeline. The pipeline of the DPU has 14 stages, and we also have 2 SRAM-based memories. One is for instructions, and the other one is for operands, as you may remember. By using this DMA engine, we can move operands between WRAM and MRAM, and we can also move instructions from MRAM to the IRAM. If you want to learn more about the AppMem PIM architecture, you can wait for later lectures of this DNS on processing in memory, but you can also read or benchmarking paper or watch the longer talk related to it. And today we are going to talk about Samsung FIMDRAM, which was the first processing in memory architecture that Samsung announced earlier this year in February, actually. And as you can see on the screen, this processing in memory architecture is targeting AI applications, and that's the way it's designed. Over the course of this lecture and also later lectures as well, we will keep talking about real-world processing in memory architectures, and we will talk about similarities and differences between them. So for example, we have the first difference between the Samsung FIMDRAM architecture and the AppMem PIM architecture. One first difference is that the Samsung FIMDRAM architecture is targeting AI applications, which have as particular characteristics. We are going to talk very briefly about that today. And on the other hand, we have the AppMem PIM architecture, which is more general purpose. And actually, that's one reason why it provides one richer ISA than the Samsung FIMDRAM. If you want to learn in depth about this Samsung FIMDRAM, I would definitely recommend you the first paper that the Samsung presented at ISSCC 2021. That this was in February, and later in June, they presented this hardware architecture and software stack for processing in memory based on commercial DRAM technology. They presented this at ISCA 2021. Feel free to ask me any questions over the course of this meeting. Okay, before we go into the details of the architecture itself, let me remind you that Samsung FIMDRAM, at least the first realization of Samsung FIMDRAM, has been built using HBM memory. So that's why I think it's good to give a little bit of background about HBM memory. The HBM memory is a 3D stack memory organization, as you may know, and it consists of multiple DRAM layers to store data and a buffer layer. The buffer layer contains the input-output circuitry and some additional features such as self-testing or test debug features. By using the I/O circuitry, the host processor, either a CPU, a GPU, or an FPGA, can access the data in the DRAM layers. The way that the DRAM layers and the buffer layer communicate with each other is using like vertical connectors that are called through silicon vias, or TSVs. And here you can see kind of a pictorial representation of a system in package containing a host processor. As I said, this can be a CPU or a GPU or something else. And then we can see on the left and on the right, two stacks of HBM memory. In this case, as you can see here, it's composed by several DRAM dies that are stacked on top of each other, and they all are on top of this buffer die. And these vertical connections that you can see here are the TSVs. The buffer layer is connected to the host processor via a silicon interposer. The good thing of using this silicon interposer instead of directly routing the bus on the board is that we can directly bring the TSVs from the buffer die to the host processor, and this increases the available bandwidth dramatically with respect to DDR type memories. One HBM2 comprises 4 pseudo channels, each with 4 bank groups. So here on this part of the image, you can see one of the HBM DRAM dies, and as you can see, it's composed by 4 pseudo channels. This would be one pseudo channel, and and here we have another one, third one, and fourth one would be here. And for each pseudo channel, we have 4 bank groups, and inside each bank group, there are four banks as well, as you can see on the screen. In the middle of the bank group, we have the bank group IO, and then in this middle part of the HBM DRAM die, what we can see are the TSVs that go from the upper layers to the bottommost layer, which is the buffer die, as we already said. And then we can take a closer look at the internals of each of these banks. And inside each of the banks, what we find is several DRAM subarrays that are connected to local sense amplifiers, what we typically call the local row buffer. We may have several of these, one for each of these subarrays, and then the data, the different data in different word lines and bit lines of the subarray is accessed by the addresses indicated in the row decoder and the column decoder. Okay, and one last thing is that in order to move data in and out of the DRAM bank, we have these IO sense amplifiers. This is what we typically call the global row buffer, right? And from these IO sense amplifiers, we can move the data to the buffer die for the access from the host. So if we take a look at a single access to this HBM memory, what we can see is that we can obtain from memory up to 256 bits, a data block of 256 bits over 4 64-bit bars over one pseudo channel. So if we have one pseudo channel, we can read 256 bits at once, or in 4 bars of 64 bits. And HBM is already being used in many commercial products. Actually, I wanted to show you a couple of them. One of them is the NVIDIA GPUs. This is the A100 GPU, which is the most recent architecture, as you may know already, but earlier versions of the NVIDIA GPU architecture already included HBM memory, starting from Pascal architecture back in 2016. After that, we have seen Volt architecture, Turing, and now these Ampere A100. And here, even on the chips, you can identify the central part is a GPU, where the GPU cores reside. And here, these 3 rectangles on the right and on the left are 6, in total 6 HBM stacks. And actually, you can even look at it closer and find them here. These are 3 of these HBM2 stacks, and here we have other 3. As you can see, we access each of them via 2 memory controllers. And here in the middle, you can see the you can find the whole array of GPU cores that access to these HBM stacks using the memory controllers. And it's not only in GPUs, we can also find HBM memories in FPGAs these days. This slide is from a recent work of us, Nero, an accelerator for weather prediction modeling. And here in this study, we used two different FPGA-based systems with two different types of FPGA boards, one of them featuring an HBM-based memory, as you can see on the screen, and the other one using DDR4 memory. The paper provides interesting insights about the benefits that you can obtain using HBM memory in your system instead of traditional DDR memories. This is the paper, and here you can find a link to the paper. And here I can show you very quickly some of the details of this Nero accelerator. Usually the FPGA is connected to a host processor. In this case, it's an IBM Power 9 processor. Here in the IBM Power 9 processor, we have the Cosmo API running, which is the API that allows the user to connect this Cosmo weather model running on the host CPU with the accelerator that is going to accelerate certain operations, certain functions of the Cosmo weather model. And host and accelerator and FPGA are connected via a coherent accelerator processor interface called CAPI2. There is a newer version of it called OpenCAPI, but it's also a coherent interface, and it has similar characteristics, including also a little bit more speed up, a little bit more transfer speed or bandwidth here in the bus. And then if you take a look at the FPGA, at the design on the FPGA, well, we use the Snap framework to orchestrate the whole development and integration in the system. And here on this right-hand side, you can see the different processing elements implemented by the Nero accelerator and some on-chip memory as well. These processing elements have access to the HBM stacks, two HBM stacks in this FPGA via an HBM memory controller. And as you see, we have the 16 pseudo channels for each of these stacks. And this is a newer version of this work. Well, actually, this work includes not only the a few more details about the acceleration of the stencil computation on weather prediction, but also an additional application, which is a bioinformatics application. So, and actually this may be even lighter to read because it's more like a magazine-like type of paper. So, well, for sure, quite an interesting reading. Okay, so after reviewing HBM, let's start talking a little bit more about the FIM DRAM architecture. So HBM bandwidth is not enough for many ML workloads. And actually, this is something that we can observe in our daily work with GPUs, for example. Many workloads, even though they are already using HBM memory, they are still, they are still memory-bound architectures for many workloads. And if we focus on linear algebra workload like BLAS routines, we will see that most BLAS 1 and level 1 and level 2 routines in BLAS are memory-bound. Only BLAS 3, there is much more data reuse in these routines, and they are typically compute bound, as you may know. So for this type of ML workloads, and these type of patterns are very frequent, for example, in machine learning inference, it's desirable to obtain higher bandwidth and to provide the processing elements with higher bandwidth. So in the conventional usage of DRAM memory, that if it's HBM or DDR4 or something else, usually the way to access data is with the von Neumann bottleneck, with the von Neumann model, as you already know, and we are bottlenecked by this memory bus and this channel here. So the key idea in FIM DRAM is to optimize or avoid all these external off-chip data movement and optimize the applications that are memory bound by exploiting the much higher memory bandwidth that is achievable, that we can obtain inside if we operate inside the memory itself, right? So we are moving from this, let's say, monolithic approach where all the processing is here in the execution unit of the host and all the data is residing on the other side, on the right-hand side on this memory. We are moving to a more distributed approach where we have processing elements or execution units, which are these greenish rectangles that you can see here connected to each of the individual banks. And this is definitely the approach that FIM uses. FIM, and you probably are already familiar with this figure here because I think I've shown it in previous slides, in previous lectures. FIM is based on HBM2, and as you may remember, there are a few layers that are core die layers, HBM2, so they are pure storage, and there are also other layers that are FIM capable. So they are including these PCU blocks that are the processing elements. And as you can see in this layout of one of the layers that talks about the chip implementation or in full custom and digital RTL, you can see that here between two of these banks, we have bank 0, and here we have bank 1 of this pseudo channel 0, which could be composed by these 16 banks here. So in the middle of these two banks, we have one PCU block, and this PCU block has access to all the data in bank 0 and bank 1. So you can also identify other two pseudo channels here on the right-hand side, and here in the middle we have the TSV and the block for peripheral control. And then in this slide, we go closer to each of the different banks. This is a conventional HBM2 memory, and here we have FIM. And in the end, the goal of this slide is to just compare the two designs. We can see a lot of, essentially the layout is the same. The only thing is that here, this area where we can only find the I/O control in one conventional HBM bank, we see the PCU for bank 0 and bank 1. As I said, the PCUs are the processing elements, and here you can see it a little bit bigger. We have bank 0, we have bank 1, we have column decoders here, input-output sense amplifiers, and then connected to them, we have the PCU block for bank 0 and bank 1. So when designing this FIM architecture, Samsung folks have had several design goals, or two main design goals. The first one is to support both conventional DRAM and PIM DRAM mode for versatility, because you may want to use this memory for calculations or for computation or not, and also to be compliant with the standards. And then second goal is to minimize the engineering cost of redesigning DRAM banks and subarrays. And if you want to minimize that engineering cost, the best thing you can do is just don't touch the internals of the banks. And that's why instead of placing, one possibility could have been to place the processing elements even closer to the cell array. What they decided is to place these SIMDs, FPUs near the I/O sense amplifiers, and this way avoid the need for redesigning the internals of the DRAM banks and the subarray. So that's, I think, one first observation in this slide, is that this idea of placing the processing elements near the banks but not inside the banks, it's kind of a common trend in the commercial processing in memory systems these days, because if you remember, the UPMEM PIM architecture also places the DPUs near each of the banks. And the one difference is as well that while in FIM we have one of these execution units per every two banks in AppMem, we have one DPU per bank. So that's, as I said, the PIM unit at the IO boundary of a bank, one PIM unit for each two banks, and then we can go closer and take a look at the execution units, and we see that these are SIMD floating point units. And in total, this is a SIMD unit with in total 16 lanes, as these two that you can see here. So in total, we have 16 of these, and each of them is 16-bit floating point unit. The reason to choose 16-bit is because that's probably a precision that gives a good trade-off for many machine learning workloads. And that's here, the fact that we are using here SIMD FPUs is also one difference with the AppMem PIM architecture, which, as you may remember, uses single thread. So it's a in order processing element, in order core that it's multi-threaded, but it allows the concurrent execution of threads in time by issuing instructions from different threads onto the pipeline. Remember that pipeline of 14 stages. While here, besides being pipeline, as we will see, each of these SIMD FPUs is exploiting the special parallelism that the machine learning workloads may have. By the way, if you want to learn more about SIMD processing and also GPUs, which are like the most representative SIMD processors that we can find these days, I would recommend you some lectures. But before that, I want to very quickly review what's the meaning of this paradigm, SIMD. Many of you might be familiar, if not all, might be familiar with this FIM's taxonomy of computers that classifies machines into 4 different types. The first type is single instruction, single data. This resembles a single thread of execution that is operating on a single data element. The second one is the SIMD paradigm, where single instruction operates on multiple data elements. And here is where we have SIMD processors, and these are the, say, 2 classical types of SIMD processors, array and vector processors. And then we have 2 other classes in this taxonomy, MISD, which is multiple instructions operating on a single data element, and MIMD, multiple instructions operating on multiple data elements. And now we want to focus on SIMD engines and SIMD processors. They exploit data parallelism. In data parallelism, concurrency in the execution comes from performing the same operation on different pieces of data. For example, the dot product of 2 vectors, or in image processing, if you have like multiple pixels of an image and you have to apply exactly the same operation, like for example, brightness adjustment on every individual pixel of the image, right? So we can apply exactly the same sequence of instructions to multiple data in an image to multiple pixels. And this is different from other types of other ways of exploiting parallelism. For example, in data flow, concurrency arises from executing different operations in parallel. It's more similar. Instead of data level parallelism, we could be talking about task level parallelism here. And it's also different from thread or control parallelism, where concurrency arises from executing different threads of a control in parallel. In SIMD, we exploit operation level parallelism, and one operation might be one instruction or might be a sequence of instructions, but this operation is applied to different pieces of data, and exactly the same operation is applied on them. So we can say that this operation level parallelism is a form of ILP, where instruction level parallelism, where the instruction is the same across all the data elements that are processed. The way that we can build a SIMD machine is by either exploiting the concurrency in time or in space. We typically have in a SIMD machine multiple processing elements And we can talk about time-space duality, depending on how we exploit these multiple processing elements. In an array processor, what we typically have is that an instruction operates on multiple data elements at the same time using different spaces or using different processing elements. In a vector processor, an instruction operates on multiple data elements in consecutive time steps using the same space. And here you have a pictorial representation of both an array processor and a vector processor. As you can see in the array processor, we have 4 processing elements that are all equal to each other, while in the vector processor, we have more specialized processing elements, for example, for load, addition, multiplication, or store operations. Here we see an instruction stream. This is a sequence of, it's kind of a pseudocode of an instruction, a SIMD instruction stream. The first instruction is a load instruction, and access to memory to read 4 elements of one array and store them in a vector register. Then an addition where we add 1 to each of the elements in the vector register. Then we multiply by 2 each of these elements. And finally, we store the 4 elements of A into the original location in memory, right? So how do we execute these on an array processor and a vector processor? Well, in the array processor, because the 4 processing elements can operate the same way, we can perform the 4 loads in parallel. So they are exactly the same load, so there's exactly the same operation at the same time. And then we would execute the addition, then the multiplication, and then the store operation. However, in the vector processor, because we have 4 processing elements and each of them is specialized, what we are going to do is loading first element 0, and then we can load element 1, but right after having loaded element 0 in the corresponding part of the vector register, we can start with the addition, and then we load element 2, we add for element 1, and we'll multiply for element 0, and so on. And this way we create this pipeline of instructions in each of the individual processing elements. So you can already see the differences between the array and the vector processor, how the architecture, the microarchitecture could be different, even though we may program them in the same way or very similar way. So in the array processor, we have the same operation at the same time. In the vector processor, we have different operations executed at the same time. And in terms of space, in the array processor, we have different operations at the same time on the same processing element, while in the vector processor, we always have the same operation in the same space, in the same processing element. So these are like 2, let's say, general versions of SIMD engines or SIMD processors, the array and the vector processor. As I said, if you want to learn more about SIMD processing, I would recommend you this lecture from Professor Mutlu. He taught this spring semester. And you may want to learn a little bit more about GPUs. GPUs in the end are SIMD machines. The only difference, or the key difference with respect to traditional SIMD machines, is that they are not programmed using SIMD instructions. They are programmed using threads. It's the SPMD programming model, single program, multiple data, where each thread executes the same code but operates on different pieces of data. And each thread has its own context, right? It can be treated, restarted, executed independently. That's something, well, we will for sure talk more about the SPMD programming model in later lectures, because we are going to introduce programming of processing in memory systems, and in particular, we will focus on programming of the AppMem PIM system. As you will see, programming the AppMem PIM system is it's quite similar to programming a GPU, because both use the SPMD programming model. There is one difference between these two, and one difference is that while in the AppMem PIM programming model, we are only going to use single individual threads we program individual threads, and then these individual threads are scheduled and executed independently of each other. In the GPU, each of these threads belong when they are executed on the hardware. Each of the individual software threads that we program when we are programming a GPU, they are grouped together to create kind of SIMD units that we call warps for in NVIDIA terminology or wavefronts in AMD terminology. But in the end, the idea is pretty similar as well. The way we program them is using the SPMD programming model. In the GPU, some of these groups of these threads, in NVIDIA GPUs, for example, a warp is typically 32 threads. So 32 threads are collocated together and they are executed they are executed in lockstep on the GPU hardware. And that way, from that point of view, they are going to behave the same as a SIMD unit, because each of the warps, it's going to execute SIMD instructions in some way. So a warp is essentially a SIMD operation or a SIMD instruction formed by the hardware. You are already familiar with this picture of the NVIDIA A100 GPU. I wanted to show you it again for you to see how many cores are here in the current, let's say, most powerful A100. There are 108 cores on this layout. There are 128 because that would be like the full-blown chip. And if we take a closer look at each of these cores in the NVIDIA A100 GPU, what we see is something very similar to what we saw when we were talking about array and vector processors. We can find multiple processing elements. Some of these processing elements are of the same type, while we also have processing elements that are specialized for different types of operations. Like, for example, here we can find 16 int32 processing elements. Here we have 32 floating point 32, floating point 64, we have load store units, we have special function units, and finally, we also have these tensor cores that are specialized for machine learning computation, neural networks, deep neural networks, and so on. And if you want to learn more about GPUs, I would recommend you this longer lecture that I gave also in the spring semester, or if you want like a shorter version of those lectures, SIMD processing and GPUs, I can recommend you this one that I gave a few days ago in our other PIS in the heterogeneous systems course. So after reviewing SIMD processing and learning a little bit about GPUs, about the fact that GPUs in the end are like SIMD processors. By the way, GPUs combine SIMD processors and also combine fine-grained multi-threading, which is something that I also introduced a couple of lectures ago when I was explaining the architecture of the UPMEM PIM system. So that's why GPUs are so interesting from the architecture point of view. But if we go back to FIM DRAM, you remember this figure with the different banks in the HVM DRAM die, and then in each bank we have cell arrays, we have column decoder, write drivers, input output sense amplifiers, and then we have the processing elements. The processing elements contain, or the PIM units, as they are called here in this slide, contain registers, and then they contain the floating point units, in total 16-bit lanes, as we said before. So the PIM units respond to standard DRAM column commands, and actually the way you will see in later slides, the way instructions are issued on the pipeline is when the memory controller issues a DRAM command, either read or write, and this is good because this makes that the FIM DRAM system is compliant with JEDEC standards, and we can use a modified JEDEC controllers to operate with FIM DRAM. And another important thing is that this wide SIMD operation is commanded by a PIM instruction, is executed in a deterministic latency in a lockstep manner. Remember that this is a SIMD unit. It has 16 of these FPUs, and whatever we execute inside these 16 FPUs makes progress in lockstep. So for the 16 data elements that we are operating on the 16 different lanes, we make progress at the same time. That's why we talk about lockstep execution. If we go back to the idea of the GPUs I mentioned, I think that warps are also executed in lockstep. And a PIM unit can get 16-bit operands from the input-output sense amplifiers, from a register, or the results bus as well. As you see, each individual FPU can get data from the input-output sense amplifiers, from these global sense amplifiers, row buffer in the bank, or from these registers that the PIM unit has, or either the result bus that comes from the FPU itself. And here in this slide, we see how we can exploit the bank level parallelism, or how FIM allows us to exploit bank level parallelism. In the conventional standard DDR device, we only access one bank at a time, right? Here, the key idea is to, as I said in the beginning, is to be able to operate on multiple banks at the same time, because this way we can exploit much higher bandwidth. In total, we can exploit up to 8 times higher bandwidth than if we use the conventional operation mode of the HBM memory. One interesting observation here is that even though one stack has 16 or we have 16 of these pseudo channels, we don't obtain 16 times higher bandwidth, but only 8 times higher bandwidth. And the reason is that in order to get access to the data, we have to send 2 consecutive read or write commands to each of the banks, right? And the standard imposes twice the latency when we perform 2 consecutive accesses to the same bank. It's twice the latency than if we issue accesses to different banks. So that's why we have to wait twice as much time to be able to activate one row in one bank again, and this or read from one row in one bank again. And this is why instead of multiplying this the bandwidth by 16, we're only achieving 8 times more bandwidth. And as you can see on the figure, there are 3 different operation modes. In the first operation mode is the default one, conventional DRAM operation. There is a sequence of activate and pre-charge commands that the memory controller can issue to the HBM stack in order to move from the single bank mode to the all bank mode that allows access to multiple rows in all banks. And then from here, we can go to the AV PIM mode by activating one specific flag that is stored in a specific row in memory. And this way, we activate this AV PIM mode that it's where we can start running programs on the PIM units, and the execution of instructions in the PIM units is going to be commanded by the memory controller. And every time that the memory controller triggers a issues a memory command, this will trigger a new PIM instruction that is read from one particular register in this CRF area. We are going to talk about these registers very soon. But then you may be asking yourself, how is it possible to enable a processing in memory system on an HBM memory or other type of DRAM memory without modifying the memory controller at all? So the key mechanism that enables that is this internal FIM controller that controls the FIM mode without any modification of the host processor hardware, of the memory controller, or of the host processor, or any other component. I don't want to go into the details of this control circuit, but here you can identify the PCU block. This is the unit that we are going to discuss in more detail, that is composed by an interface unit, an execution unit, and a register file. And here inside the internal FIM controller, you can see that it receives the commands from the memory controller, and it also receives the addresses from this address decoder. We have column addresses here, we have row addresses here, and bank addresses over here. And there is also a clock divider that is dividing by 4 the main clock of the HBN stack in order to send this PCU clock to the interface unit and the PCU block. And yeah, I think so. And here you can see also how to so when we are operating in FIM mode, either we access the even bank or the odd bank. Remember that each PCU block is connected to 2 banks, for example, bank 0 and bank 1. So bank 0 would be the even bank, bank 1 would be the odd bank. Okay, so let's take a closer look at the programmable compute unit. Here you can see a quite simple figure, but it's already good to identify all the different components in this programmable compute unit. The first thing that you can see here is the control unit, that it's like the instruction sequence manager, is the unit that receives the commands and internal commands that come from the FIM controller that we have just seen in the previous slide, and this one decides what's the next instruction to execute. The instructions are in this register file here, in particular in this CRF group, as we will see in later slides. But for now, what we can say about this pipeline, about this PCU, is that it has a pipeline of 5 stages. The 5 stages are, first of all, fetch and decode stage. Then there is an optional stage depending on the specific instruction that we execute, on a specific version of some arithmetic operations. As you will see, some of them read operands from registers, other read other of these instructions use operands directly from memory. So that's why this step 2 gives us the possibility of loading 256 bits of data from either the even or the odd bank, right? And this way, 256 bits are what we need to operate on the 16 units of 16 bits each. And then we have the multiply stage, and then we have the add stage. Recall that in machine learning workloads, the most widely used operation is the multiply accumulate operation or multiply add operation. Both can be executed with by using these 2 stages of the pipeline. And finally, we have a write back stage to the GRF, which is where we store the general purpose, where we have the general purpose registers, and where we store the partial operations, partial sums coming from these multiply and add floating point 16 units. Okay, let's go even closer to the programmable compute unit. Here we can find the interface unit that is to control the data flow. We're receiving all these different signals from the FIM control unit. Here, for example, we can see the PCU clock, here the line for FIM mode, and then row and column address and so on. In the middle, we can identify the execution unit. The execution unit contains a pipeline decoder for this first stage where we fetch and decode the instruction. Then we have the multiply array, then we have the add array. So these are 16 multipliers here, 16 others here, and then yeah, we have the CRF sequencer, which is like the unit that has access to the CRF where the instructions are stored. And you can also see, well, the register file controller to access the register group and the different registers that we can find here. We have this CRF, as I said, contains the instructions from the PIM program, the program that executes on the PIM unit. One interesting observation here is that the instructions are 32-bit of size, and there are 32 entries in this CRF. So which means that we can only keep here 32 instructions, right? So yeah, that's why we will need, for example, as you will see next, some instructions to jump if we have to repeat a certain sequence of instructions, or we may need to load the new instructions here. If we want to execute a different operation, different computation, then we have the GRF, the general register file for weights and accumulations. So typically, if we are executing a deep neural network, what we are going to typically load or store in the GRF, either A or B. You see that there are two different ones coming from the two banks, even and odd. So what we are going to typically store here are the weights of a filter, for example, and also partial results that come from the execution unit from this pipeline. And then we finally have this SRF. We have two different groups of this source register file. As you can see, this is for constants for the multiply accumulate operation, and here the figure shows what's the width of the individual registers and how many registers we have. So in the GRF, because this is used to feed the execution unit, and we have 16 lanes in the execution unit, we need 256 bits, and in total we have 8 registers, 8 of these vector registers here in GRFA and in GRFB. And this is the instruction set. It's, as you can see, is quite short. Instruction set architecture is RISC style because instructions are pretty simple, and they are 32-bit instructions, as I said before in the previous slide. And here you can identify different types of operations. We have, or instructions, we have the pure ALU instructions or arithmetic instructions, which are floating point operations. Here we can find addition, multiplication, multiply, accumulate, and multiply, add. Notice that these two both use both the multiplier and the other. The difference between them is whether you store the result in the same register, the value of which you are adding to the result of the multiplication, or in a different one. That's the difference between multiply, accumulate, and multiply, add. And then we have some data path of the operations or data path instructions. We have move, which is to load and store data coming from the banks into so it's a move data. Yeah, it's to move data either from the banks or from registers, from one register to a different one, or field, which is to copy data from a bank to the general register file. And then we have the control path instructions. We have NOP instruction in case it's needed. It kind of includes, so it inserts 5 cycles that are, let's say, NOP cycles, so completely empty cycles. Then we have the jump instruction that I mentioned before, and then we have this X instruction when we terminate a program. And there are different combinations for these instructions. This is a different table, but essentially contains, well, similar information. This is for the arithmetic operations and the move operation. By the way, the move operation can also execute the ReLU operation if one specific bit is enabled when we are moving from one operand to to one destination. So from one source to one destination. And here in the table, you can see the different instructions, these 5 instructions, different operands for the SRC0 or SRC1, because they are using 2 operands each. And as you can see, they may be coming from different places, either GRF or SRF or the bank, and then where the result is stored. So for all of these, there is a number of combinations. So there are, let's say, different instructions depending on where the data is coming from or where the result is going to. And here you can see the instruction formats for the 3 types of instructions. First, 4 most significant bits are the opcode of the operation, because we have in total 9 operations. 4 bits is more than enough to identify the specific operation, and then you can identify the different fields of the format: destination, source, either source 0, or here we have 3 possible sources, and then we have the register numbers in case that we are using registers here, or what is the specific identifier of the destination. Then there are also some unused bits, which are these marked U here. And then remember that I mentioned that the move operation can also execute, not only move, but also execute these ReLU operations. So that will happen in case that this R bit here is set to 1 in the specific format of the move operation, which is this data movement format. Okay, so how does the execution happens in FIM DRAM? What's the operation flow? So we are going to very briefly take a look at some operation sequence for example, a matrix vector computing. So here the input and the output data are accessible to the host in the conventional DRAM operation. So notice that if we want to compute, so if we want the host to access, we will have to use the memory in the single bank mode. If we want to compute, we will have to go to this all bank PIM mode. So what this means is that the host can access the data in single bank mode, while in the AV PIM mode, we have the compute units accessing the data. And from that point of view, it's also similar to the way that kernels are executed on AppMen DPUs, because as you may remember, we talked about these 2 lectures ago, the execution of the DPU kernels happens between accesses of the host CPU to the PIM enabled memory, to the MRAM bank. So in that sense, this is similar. So yeah, so we could start with some power up and initialization, and then we decide whether we want to use the HBM stack for computation, or we want to use it for conventional DRAM operation. So we are more interested today in the FIM DRAM computation. So because we want to perform computation, first thing to do is to store data into the cells. This is the input data that we need for the matrix vector operation. That's the access that we perform for writing the inputs from the host. That's why it's color. This step here is colored with this light blue, and then we change the mode. We go from the normal operation mode to the processing in memory mode, and then we can start executing instructions. So you can see that first of all, we need to program the register file. We will store their instructions, and we will store their weight data for the filters of the neural networks, and then we start the execution on the PIM units, right? And as you can see, the way that we execute instructions, it is by sending DRAM commands from the memory controller of the host processor to the specific bank. So actually to all banks, because here we operate in all bank mode. And as you see, so we would first issue and activate, and then a series of read or write commands, and for each of them, the program counter is going to increase by 1, and we go and fetch a new instruction from the CRF, from the control register file, right? And here you can see how the 32 instructions that are stored in this CRF are going to be fetched from the CRF one by one and executed on the pipeline cycle by cycle. After we terminate the execution. This may be more than 32 instructions, as I said, in total executed in this FIM mode. The reason is that some of these instructions may be jumps, and we may repeat this sequence of 32 instructions more than once. And after that, we will exit the FIM operation, the processing in memory operation, and then depending on what we want to do next, we may load new instructions to the CRF registers, or either go back to the normal mode and then transfer the results to the host, or read the results from the host in the normal mode. Okay, there is one challenge in the design. This is something interesting for you to, if you want to learn the details, go to the original paper by Samsung. But one challenge is that DRAM commands may be reordered. And one possibility of avoiding this reordering of DRAM commands in the memory controller is to use fences. The problem with fences is that they are costly in terms of performance. So that's why Samsung folks came up with something called the address align mode, which is a way of solving this challenge. And what they essentially do is somehow coalescing 8 multiply accumulate operations with just 2 PIM instructions. And so every 2 PIM instructions may look like this. Here you can see a MAC instruction. The format is, or this syntax here resembles the format that we have just seen a couple of slides ago. And then you can see the jump instruction. This -1 must probably mean that we are going back to the previous instruction. And each of these MAC operations is decomposed into different read, so activate and read commands that are going to issue the different MAC operations that we want in the pipeline to happen. And here we can take a look at the different data movement modes, right? The data flow is controlled by the operation mode, either single bank or multiple bank and PIM, and one specific bit in and row address 13, depending on what are the first of all the operation mode and the value of the actual command, either read or write, and the value of the 13th bit number 13 of the row address. We see different ways of data movement. It might be in normal mode or in FIM mode. Here on the left part of the figure, of this figure, you can see the number 1, which is data write to cell array. So as you can see, it's coming from the TSVs to one bank to write some data from the host, or to read the data, right, from this bank to the host via the TSVs. Then we have the other 3 modes of operation, 5, 6, and 7, that either move data from the PCU block to the cell array. So this is write operation from the PIM unit to the bank, or data write from the to the PCU register. So this is when we so we are writing from. So this number 6 is represented by this arrow. So this is coming from the host. So what we are doing with this operation mode 6 or data flow mode, data flow mode 6 is writing either in this PCU block or this PCU block to the registers of of these PCU blocks. For example, this is useful to load weights into the GRF, in the general register file, or instructions in the CRF. And then we finally have this mode, so this version or mode 7, that is the data movement from the cell array to the PCU block. So that's why we see here from the bank to the PCU block. So these are the two directions from the PCU block to the bank, either 5 or 7, or from outside writing when we are in PIM mode to the registers of the PCU. And here you can find a comparison. It's a kind of a key feature summary and a comparison table from one of their papers. They compared to other processing in memory systems, and including the PIM processing in memory system. I don't think that this is a, let's say, rigorous comparison table. I just wanted to have this table here because it comes from the paper. But I don't think that we can compare these two architectures directly. The main reason is that they are designed for different purposes. While FIM is a much more application-specific or domain-specific architecture that is specialized for certain operations, say certain operations like multiply, accumulate. PIM provides a much richer instruction set, as you may remember, and so it's more general purpose, and that's why I think it's not, we are not comparing apples to apples here, but still I think it's interesting to see these numbers next to each other, right? So one, PIM is based on DDR4, HVM is based on FIM is based on HVM2, which, by the way, I think that both of them are perfectly interchangeable. You can for sure build something like FIM using DDR4, or integrate a similar unit like the DPUs in an HVM memory too, near the bank. That's something that is doable. You can see here also what's the memory density of the two PIM architectures, data rate, what's the maximum bandwidth you can achieve is much higher bandwidth, of course. HVM2, this is for a single DIMM, but you can also think about what would be the total bandwidth that you can achieve when you have in a PIM system, you have more than one DIMM. You can have up to 20 DIMMs. Remember, 40 ranks in the larger system that provides these days, and probably you are not going to have so many cubes of HVM, especially because one reason is the additional cost that this memory has. Then you have number of channels, 16 per DIMM, in PIM, 8 per cube, and number of processing elements or processing units. This is interestingly is the same number per DIMM and per cube, but now if you compare these two types of processing units, you will see that they are completely different, right? While in one place we have in-order processors that execute multiple threads and issue instructions from these threads one after the other. On the other side, we have a shorter pipeline of only 5 stages, but each of the execution units is a SIMD unit that can execute up to 16 threads or 16 operations at the same time. And then processing speed, in this case, it's also different. Actually, the reality is that they are closer than what it looks here, because this 500 is kind of a future frequency value for PIM, something closer to the actual PIM DIMMs that are already in the market is 350 megahertz, but I believe that next generation will be a little bit faster, probably 400 megahertz. And then peak throughput is also quite different. And actually, here, yeah, so it's in the end peak throughput. So I don't think that this is something that it's really, so it's good to have it as a theoretical maximum value that to consider and aim for it for sure, but it's always necessary to move data, even if it's from the bank to the register file or in the PIM architecture, from the MRAM bank to the WRAM, there is always data movement, or also in the PIM architecture from the WRAM to the registers to perform operations in the pipeline. So in the end, I think that these are like more like theoretical numbers that are not so representative or not so important at this point. And then regarding the operation precision, well, yeah, so for sure, FIM DRAM is floating point 16 bits. PIM supports many more data types than integer 8, right? Actually, the normal in normal operation, you would be using 32-bit integers, I would say, because the registers are 32-bit registers. But there's still probably the reason why they put here this int8 because the only multiplication the only multiplication that the PIM DPU supports natively is for 8-bit integers. Remember that 32-bit multiplications are implemented using a routine that uses repeatedly a shift and add instruction. And probably that's the reason why they put this here. But as I said, PIM supports other data types like 32, 64-bit integers and both single and double precision floating point operands. Okay, so I think we are more or less done with the explanations regarding FIM DRAM. I hope you find this useful. And if you want to know more details, feel free to contact me. I would be glad to clarify as much as I can. But I would definitely recommend you to read the two papers, the first one in ISSCC and the second one at ISCA, presented at ISCA this year. In our next lecture, we are probably going to talk a little bit about the other proposal from Samsung, which is AXTIM, and probably more as well. We may talk about more real-world PIM architectures or prototypes of real-world PIM architectures. So yeah, it will be really nice to have you in later meetings as well and in later lectures, and we will keep giving lectures every week, and for sure, yeah, we will do our best to give you good updates about the state of the art in processing in memory, and that's all for now. I don't know if you guys have any questions. Juan, you are in the meeting. Thank you very much for joining. Yeah. Are you monitoring the YouTube chat? I don't know if there are any interesting questions there.
I can have a quick look.
Please do.
So there's a bit of activity on the chat, but
I'm checking too. I don't think that there are any.
Yeah, I don't think so. Yeah,
there is some discussion there, which is good, but
yeah,
I think there are no really questions today.
For you at the moment. Yeah.
Okay, thank you very much. Thank you very much, John. Thank you everyone for your attention. As I said, I hope you found this lecture interesting, and I hope to see you again in our